So, now we will discuss about different types of light sources in terms of semiconductor devices first, then we will go to some other type of light sources which are used for biophotonics application etc. So, of course, laser light emitting diodes LEDs are here, and some of the different versions of LED light emitting diodes results in either a laser diode or superluminescent emitting light emitting diode. Okay. So, now what are the what makes light emitting diode as a laser diode or SLED etc. This pictures which are shown over here are basically represents the configuration of such as light sources. Now, light emitting diode emits light in all different directions. There is no gain, no feedback. You may not be knowing what exactly it means. We will try to see it in the next few minutes. And then there is SLED, superluminescent light emitting diode, which is based on the principle of single pass gain. Okay. So, and and when we end up with multiple times this gain and feedback, we can achieve a laser output. As it is, if you see from these pictures, it is very difficult to find out what exactly is the difference. Of course, as only one thing that you can see is that the light over here is diverging in different directions. Light over here is emitted in one particular direction. Secondly, if we see the LED or SLED, it has a spectral bandwidth. Okay. So, x axis is wavelength, y axis is the emission intensity, and it has a bandwidth. Okay. This bandwidth is decided based on the band gap configuration. Okay. And we will try to estimate what would be this bandwidth, approximate bandwidth, which is around, depending upon wavelength, again it will vary, few tenths of nanometer order. Okay, bandwidth will be available. However, when we go towards laser diodes, light emitting diode, if it gets converted into laser diode, the bandwidth is quite narrow. Okay. Here the spectral bandwidth are quite narrow. Okay. We will achieve very narrow spectral bandwidth lasers, as well as we will also achieve some of this longitudinal modes as the output from this laser diodes. Okay. Now, what makes it what are the configurations? We will just try to see in a simple way. So, the next one. So, here if you see generally I am going to now first talk about how laser light emitting diodes work. Okay. So, we know that when we go with doping, n doped or p doped, accordingly the electrons located at a particular energy levels will be slightly different, and we can see that the Fermi level also depending upon if it is n doped, Fermi level will be nearer to the conduction band, and if it is p doped, Fermi level will be nearer to the valence band. And it is not very easy for electron to climb up and get diffuse and go through this diffuse and this layer. Okay, basically. So, on the other hand, when we apply forward bias, when we apply forward bias, that means now electrical field right, due to the potential what we apply, there is some electrical field acting on it, is not it, and that electrical field is responsible in terms of the current will in forward bias, the current will go through this, electrons will move and then they will cross this, right, PN junction, right, and because of this, this crossing is happening because of the forward bias, which allows because of the electrical field acting on this and the right, due to the potential applied, basically energy electrons gain some energy, right, and so that energy is something like E into difference, right, in voltage, right. So, without bias and with bias, right, potential difference will change and this energy allows electron to right, cross over, go through this junction layer, and when they goes through this junction part, right, depending upon the band gap, when electron combines with the hole, due to the recombination, the photon which is generated, okay, corresponding to this band gap is seen as the light which is emitted. On the other hand, when we apply negative, right, bias, what we will see that this energy gap increases and electron will not be able to cross over. We will not be able to see this, right, combinations of electron hole pair generated, etc. On the other hand, if we see this also, the thermal generation, okay, sometimes what happens is when we apply right, let us say I am talking about because of the temperature right, rise, etc., those that type of thermal generation allows electron hole pair combination to come into picture, okay, to take place, and because of that small reverse, right, right, current is also generated, okay. This is when we are already applying reverse bias and due to the thermal effect which is coming into picture, there will be small reverse current which is generated. However, most of the time light emitting diodes, they work with positive, right, bias and allows electron hole pair combination, this, right, approach. Now, this is very similar to, right, semi forward bias semiconductor, right, device. However, when we allow high doping, heavily doped, okay, heavily n type doped, that means it is written as n plus means the n type semiconductor material over here is heavily doped, so as to have very large density of this electrons, okay, over here as compared to the whole this pair over here. Then in this case, when we apply once again a forward bias, we will see that electron hole pair combination generates photons in different directions, okay, irrespective of the, right, the direction is immaterial, it is a spontaneous emission, okay, it results in a spontaneous emission, okay. So, this spontaneous emission is in all the different directions, okay. The photons which are emitted will have of course different right phase will be different, means this light which is emitted in different direction will not have the, right, so phase is different. So, we can say non, right, coherence, it is a non-coherent light source, okay. Phase is different, polarization state may be different, okay, polarization, so non-polarized source, okay, and the it will be emitted in all the different directions and it is diverging, okay, light source. So, very similar to what we see in the tube lights, etcetera. So, the light emitting diodes which are also right, light LEDs are also here in terms of, right, you can see the light what is. So, that LEDs are also generating diverging beam source with non coherent non polarized lights also, okay, and that is LEDs are very similar to this. Of course, the band gap decides the wavelength, and I will tell you what exactly makes the white LED, right, that we will see it afterwards, but in general this is the case. So, this is very typical light emitting diode configuration, N plus P doped or P plus N doped, right, depending upon material characteristics, P plus N plus doped also possible. Okay, I am sorry, not P plus N doped, but P plus N plus doped or N plus doped, right, semiconductor materials. As it is, when they are excited, they will emit at the junction region light which is non coherent. Okay. Now, this emission bandwidth, right, emission bandwidth will decide the photon this emission, as well as in fact, if we, I will try to see if we have some. Okay. So, in fact, I will show you now. The see, I am going to draw this basically the energy, right, band gap configuration. So, if we consider n doped material, so let us say this is y axis, this is energy, okay, and here this is energy density, okay, of carriers, okay, carriers positive means electrons or hole pairs. So, what we will see, that say conduction is here, let us say EC is here and it has. So, it will have a distribution something, oh sorry, okay, it will have a distribution something like this, okay, and EV, let us say EV is here, okay, it will have a distribution something like this, okay, and this bandwidth, okay, is approximately, okay, 2 kT, okay, right. So, K is Boltzmann constant, T is the temperature, okay, absolute temperature. So, this is holes, right, this is electrons, basically conduction bands, electrons, okay, and wavelength. So, this approximately is half kT, okay, and it is lambda t, we can say lambda p lambda, okay. So, okay, and this is lambda maybe, okay, wavelength, okay, approximate wavelength. So, 0.5, okay. Now, what I am trying to derive, that the center wavelength, okay, of a semiconductor material is decided based on the energy band gap, okay. And the energy band gap right. Basically, let us say E of photon is equal to h nu or h c by lambda. Okay, c by h c by lambda. So lambda can be given by h e of photon upon c, right. Sorry, lambda h c, I am sorry, wrong mistake, h c divided by e p h, correct. Now, if we differentiate this d lambda by d e p, so which is equal to minus h c divided by e h square, correct, if we differentiate. So basically delta lambda is approximately equal to h c upon e p h square, c p h delta e p h. Okay. Now, this delta e p h, okay, bandwidth for any semiconductor material based on this energy distribution, which is shown over here, is given by 3 times k b. This is Boltzmann constant, okay, k b into t, okay, 3 times. Right. So what we are trying to do, approximately this is 2 k b t, correct, and this lambda corresponds to e p h, okay, it is lambda corresponds to this e p h. So this e p h is slightly wider, right, because of the distribution of electrons are distributed like this. That means the bandwidth, the light which is emitted, okay, will have a certain bandwidth. Center wavelength can be lambda, but it will have a bandwidth depending upon the spread of this energy distribution, and this spread depends upon even the temperature, right, activity also. Okay, it depends upon what temperature. If the temperature is very low, the spread is going to be much smaller, okay, and if the temperature is high, the spread is going to be wider, in fact. Okay, so that is there. So we can even say that, which implies that the spread delta lambda is h c by 3, right. We can write e p h square, okay, e p h square into delta e p h 3 k b t, okay, and I'll simplify this further, okay. So delta lambda, now I know e p h is nothing but h nu, so h will get cancelled, nu is equal to c by, right. So delta 1 minute 3 k b t delta lambda, so this is e p square, so h c h nu square, correct, nu ph photon to 3 k b t. So and oh sorry, here yeah, that's correct. So this is equal to lambda square 1 upon h c into 3 k b t, can also be represented by this, right, because c by, right, nu is equal to lambda, So, by substituting C by nu as lambda, and then right one C will get cancelled, and accordingly we will get this, okay, lambda square, just delta lambda. Now, you can see that spectral width of this light which is emitted from the diode. So, diode is nothing but, let us say it is a P n plus junction. When we apply forward bias, what will happen? Electrons this, and at the junction region they will emit, they will combine with the holes, they will emit photons in different directions. Okay. This photons which are emitted will have a spectral bandwidth. Okay. So, of a particular photon may be emitted with a frequency nu 1, other one may be generated with frequency nu 2, etc. And this frequency band is decided based on this temperature band, and which indirectly determines the spectral band. Okay. So, you can see that the spectral band depends upon temperature overall, as well as it also depends upon the wavelength. So, if we are considering a semiconductor laser, or sorry, not laser, but a light emitting diode with a wavelength around, let us say 650 nanometer. So, if I consider lambda as 650 nanometer, okay, lambda in nanometer, and let us say what is the temperature, maybe we will consider room temperature 300 Kelvin, okay, 300 Kelvin. I am not remembering this calculation what temperature was used, but let us say 300 Kelvin. So, we know right T 300 Kelvin, Boltzmann constant is constant, H is Planck's constant which is constant, C is speed of light which is constant 3 into 10 raised to 8 meter per second. So, corresponding to lambda 650 nanometer, delta lambda is approximately 22 nanometer, okay, delta lambda for a direct band gap material. Okay. Now, if my the material which generates 650 nanometer is aluminum, gallium arsenide, okay, semiconductor material, it can also generate 810 nanometer depending upon the dopant characteristics. So, this dopant percentage of this, right, arsenide, etc., may be slightly different. In that case, we end up with 810 nanometer, and as the wavelength increases, the spectral width also at room temperature will be wider. Okay. If we are if we go around means around 940 nanometer, let us say 950 nanometer. Okay. So, which is again gallium arsenide. Okay. It is gallium arsenide is the material which will emit, the spectral bandwidth will be around 55 nanometer. Okay. Nanometer lambda. Okay. And so, these are all typical wavelengths I am writing. Okay. 650 nanometer is used in biophotonics, around 630 to 650 nanometer, 810 nanometer is used, 940 nanometer is used. So, 950 around that, right, wavelength, then 1500 nanometer. I am jumping, of course, in between also there are different types of semiconductor material which can allow different output wavelengths. 1500 nanometer, which is possible with indium, gallium, arsenic, phosphate, okay, P, which gives you bandwidth of 115 nanometer. It is as wide as very broad band, okay, very much broad band. So, these are all such, right, semiconductor materials which can act as a light emitting diode. Okay. Now, as I told you that in case of before we go to supercontinuum light emitting diodes, we will talk about lasers, okay, laser diodes. So, what is the difference in terms of light emitting diode and laser diode. Of course, in terms of laser output beam light, it is also a laser diode also emits light, light emitting diode also emits light. But what I told you, the light emitted from laser diode is somewhat directional, okay, it is directional. In a particular direction we will be able to get the output, okay. What it some error is there, some error is there, anything, no problem. Directional laser, right, directional. Then what else, it is very much coherent, okay, coherent. Whatever photons are emitted, they almost all these photons will be in the same phase, okay. So, phase polarization state is more or less, okay, it is polarized more or less. Of course, it is there may be some variation, but more or less, okay, and it has a narrow bandwidth, okay. Spectral bandwidth is narrow, spectral bandwidth is narrow as compared to the light emitting diodes, okay. The materials are almost the same, okay, type of let us say aluminum gallium arsenide or gallium arsenide or indium gallium arsenide material, semiconductor material same. However, what is the difference is basically semiconductor material is this p type, right, and n type, it are heavily doped, okay, they are heavily doped, okay. The density in terms of number of right carrier density is quite large, okay, heavily doped. And of course, similarly we apply forward bias. Now, what will happen when they are heavily doped and when we apply forward bias, when they are heavily doped, the conduction bands, okay, in this p type and n type are conduction in the conduction band in n type and p type in the valence band, the Fermi levels are almost submerged within this energy gap, okay. So, the Fermi levels we will see that as compared to maybe shall I draw okay. So, what the Fermi levels over here, let us say the Fermi level is here, right, shown over here, is not it. But when it is heavily doped, when n is quite large, what will happen, this Fermi level will shift to this, right, and when p is also very large, the Fermi level will shift this way, okay, and they are so much heavily doped that right, this levels will shift like this. And when we right, and of course, if I show you in terms of schematic over here, it will be okay, I will correct it, okay. So, Fermi levels are like this, okay, they are submerged in this. So, this is P plus, this is N plus, okay, and the energy band gaps right are such a way that the Fermi levels are submerged. So, this is right F, right, Fermi level is submerged. Now, when we apply positive bias to this, right, positive bias to this, what will happen, based on the right voltage what we apply, this electrons they will gain the energy, right, by the difference of right V 0 minus this V, and what will happen, the electron will be able to jump over, okay, through this junction, and number of electrons which are jumping over will be very large, okay, will be very large, and number of such holes which are also coming here, okay, they will also be large. So, what happens, the gain over here is very large, okay, the gain in the in terms of combination of this electron hole pair increases tremendously, okay. Uh, Now, not only the gain, but there is one more aspect which makes this laser diode different from LED is, if we see the maybe edge emitting diode, okay, I will draw in terms of semiconductor. Let us say I am just tilting this, okay, 10 degrees. So, this is N plus, this is P plus, okay, I am tilting it. So, we apply, correct, this is the way we, it is just tilted this part, okay. Now, at the junction region lots of photons are being emitted. They will be traveling in different directions, of course, they will be traveling in different directions. Some of them may travel this, some of the photons which are emitted here, this, they may travel this way, all different directions. Of course, still it is spontaneous, although the gain is very large, but it is somewhat spontaneous emission. Now, if we coat this edge, okay, with a mirror, okay, with a mirror, okay, mirror coating, okay, and over here with the mirror, okay. So, this is nothing but the reflector, right, high reflector with partially transmitting, very small amount is getting transmitted, okay, or I will just write okay. So, reflector, and over here it is high reflector, okay, almost nothing is transmitted, let us assume. So, here some part is getting transmitted, okay, what is generated can get transmitted, very small amount, but large amount will get reflected as well, okay. Over here large amount is getting reflected, okay. So, the photons which are emitted, some of these photons will be travelling along straight line or will interact with this, right, interface, at the interface will reflect back, right, while the photons which are travelling in other directions will not reflect back. So, the photons which are reflecting back to this region, now what is happening over here, lots of gain is there, many photons are being generated. However, the photons which are travelling back in this direction are seeing a very large gain is large, wherein it is indirectly the population of this electron as compared to the spontaneous emission, if we compare, is so large, okay. So, it sees as this photons will see this as a part of the stimulated emission, okay, stimulated emission. So, not spontaneous emission, stimulated emission, okay. So, in the previous case when the photons are emitted in all different directions, they are basically spontaneous in nature, okay, spontaneous in nature, spontaneous emission. However, when the photons are travelling back along this path due to the reflector into picture, which provides feedback, some part of the photons, some number of photons are travelling back, we will observe very large gain in this region, and it will, this photons will act as a stimulated emission region, okay. So, what will happen, other photons which are emitted due to the electron hole pairing recombination, these photons will also behave like incoming photon. Okay. We will have the same frequency, we will have the same phase, we will have the same polarization state. Okay. So, unlike spontaneous emission, where each photons emitted from the same material behave slightly differently, they have different phase, wavelength may be within the spectral range may be different, well different polarization etcetera, but when the photon is coming back as a feedback, and if it sees a very large gain, there is a chance that there will be a stimulated emission. Okay. So, what will happen once stimulated emission comes into picture, more and more number of photons will start travelling along the same line as the incoming photons, correct. More and more, the more and more photon comes in, the more and more amplification comes along the same line. Okay. So, indirectly most of the light which is emitted from this light emitting diode under this condition becomes directional in one direction. Of course, there will be some spontaneous photon emitted, okay. Always there will be spontaneous photons which are emitted, but those number of those photons is quite less as compared to the photons which are moving going to and fro, okay, and exciting few more photons while it is passing through this medium. Okay. So, this medium under n type, n plus n p type becomes a stimulated emission, and the amplification comes into picture. Okay. And so, generally we know in general in what shall I say, at room temperature, we can expect spontaneous emission and absorption to be the main phenomena. Okay. But under some special such circumstances, when stimulated emission is large, comparatively prominent or dominant, okay, we will see amplification of light, amplification coming into picture. Okay. But for that feedback becomes essential, okay, to have laser output. Okay. So, feedback is provided by the mirrors, and the population inversion in case of semiconductor material is based on doping concentration, okay, comes into picture. Okay. So, whenever there is a population inversion means more number of such excited atoms. Okay. Not here, it is not atoms here, it is all more number of electrons and hole pairs coming into picture, ready to emit photons, and in meantime a photon comes and will allow this right photons to be emitted along the same direction. Okay. So, light emitting diode in this case is nothing but laser diode, it acts as a laser diode. Okay. Now, what is laser? It is light amplification by stimulated emission of radiation. Okay. So, light amplification okay, LASER, laser. Okay. Of course, still it may not be clear to you how this phenomena is coming into picture. I will try to explain to you this similar aspects with right in when we talk about other types of laser in a slightly different way, but which will be much more convincing, okay, as compared to what is shown over here. However, in general this aspect, okay, is basically right involves a feedback. So, there is an amplification, right, but here it is a positive gain, positive feedback provided over here, okay, in this case. Amplification over here is a positive feedback which amplifies. Okay. So, the more the number of photons coming back, the amplification will accordingly go about. Okay. Of course, gain is decided by the pumping energy. So, there will be a pump. Pumping is nothing but over here is applied voltage and dopant characteristics, and right, that will decide the gain and the number of photons which are provided back in the feedback, right, cavity. So, feedback over here is based on the mirror coming into picture, okay, coating. Okay. Now, in order to see, as we can see that if it is a homo junction PN semiconductor material and it is edge coated such as like this shown over here, edge coated with mirror, we see that more or less the output is in this direction. However, still there will be lots of spontaneous emission in other directions, which is nothing but the loss, correct, it is loss, it is those photons are becoming a loss for us. And in order to generate laser output, we need to feed in a certain amount of voltage, right, in order to provide enough number of photons along this direction, and accordingly the amplification takes place, correct, that is what is happening. Now, indirectly the threshold for this lasing operation is large when it is a homo junction such material. Okay. So, when we apply when we apply, right, this, and if the edges are coated with the mirror, what we will see, the lasing operation is achieved, and but there will be some losses in terms of photons getting escaped due to spontaneous emission, but many of the photons will be along this line. So, as we go and increase the current passing through this, we will see that the output increases. So, up to certain input, right, current and corresponding output, right, intensity of the laser, right, of this light intensity, basically light intensity over here follows a curve something like this, initially spontaneous emission, okay, till it reaches to a particular level of number of photons along this line, we will see that suddenly the output increases along that direction, because more and more number of photons are being emitted along one direction, they are not getting lost in different directions, and so there is a threshold coming into picture, okay, threshold. Okay, this. So, I or input, power input. Okay. So, this power or current. Okay. So, the threshold comes into picture. Now, this threshold value, right, indirectly results in heating effect, some current is getting lost, heating, etc. We do not want such heating coming into picture, and more and more current passing will can damage, right, this semiconductor material as well. So, what we want, lesser current to pass through and better higher gain. So, for that we use hetero junction. So, this is homo junction, okay, homo junction diodes, okay, diode and hetero junction. Now, in case of homo hetero junction diode, basically the configuration, this semiconductor, this material combination configuration is such that there is going to be P plus over here, N plus, N type, etc. Okay. And P active layer also. So, there is a confining layer, and in between this is P active layer. Okay. Now, the material combination, let us say, oh, one or two more minutes, huh? We will that's because before we, so let us say this is gallium arsenide, p type gallium arsenide. Let us say this is p both right, p type, this is doped, heavily doped aluminum gallium arsenide. Okay, and this is confining layer is also heavily doped gallium arsenide. Okay, N plus heavily doped is also aluminum gallium arsenide material. Okay, and this is gallium arsenide. Okay, gallium arsenide maybe. So, it is an hetero junction such a way that, okay, all of these layers are basically having the band gap very nearer to each other. However, the band gap of this material, active material, is slightly smaller, slightly lesser band gap. Okay, so very small difference between the band gaps of adjacent layers. So, adjacent layers have slightly higher band gap, while P active layer has a slightly lower band gap. And if band gap is higher, refractive index of that material is lower. Okay. I am always, I make mistake. So, the band gap is smaller in this, right. P type active layer has a slightly lower band gap. Okay. So, refractive index is slightly higher. Okay, right. So, this band gaps are, okay, this ones are all this band gaps, okay, slightly higher band gaps, while the active layer has slightly lower band gap, very small difference. Okay. So, what will happen? Refractive index being large, slightly larger, we will see a waveguide effect, right, core and clade combination coming into picture. What it means? More number of photons which are generated will remain confined within this region, okay, and will propagate along this line, okay, like waveguide or optical fiber. Okay. Because the refractive index is slightly higher than the adjacent layers, characteristics are almost similar. Okay. Dopant characteristics, everything is almost similar, except that the band gap is slightly lesser, which makes that layer as a core, okay, and the nearby layer as clade, and the light remains wave guided within that small region, so that the photons will travel along the one path, okay, and then the feedback is provided by of course mirror, let us say this is mirror here coating, feedback is provided. So, this heterojunction, right, approach allows confinement of the light in this active layer, okay, confining the light in the active layer, confining light in an active layer, and hence the output threshold, the threshold required for laser output decreases, because photons will not escape now, spontaneous emission will start reducing, because stimulated emission will be much larger, photons will travel along this path, will get feedback, will start removing excited electrons from there to provide to get more and more at, photons along one direction, okay, right, along straight line, along this line edge, right, edge emitting this line. So, this results in the laser output with a reduced threshold and right P out sorry P in, and this is optical output, right, optical output, this is electrical input, okay, and this is over here electrical input, right, optical output. The threshold decreases by right, and hence immediately the photon output is achieved through this. Now, this whatever we just now described is generally the configuration of laser diodes. Okay. Right. So, when of course, optical diodes, light emitting diodes or laser diodes, the material may be the same, right. Only thing is the dopant characteristics are different, okay, and that allows the lasing operation to come into picture. We will try to see in the next class what are the longitudinal modes which are generated. Of course, these terms may be new to all of you. We will try to see in the next class, so that we are very clear that how exactly this laser diodes works, and we will extend this ideas towards semiconductor, so from semiconductor to other type of laser materials in tomorrow's class. Okay. Thank you very much.